Hi, it's Mr. Birdsong. Today we're going to talk about the law of induction, motional EMF, and Lenz's law in a non. I want you to imagine a circular coil in a magnetic field, like in the picture. This could be just a circle of wire laying on a tabletop, and the magnetic field through there goes straight down. What would happen if the circular coil somehow magically grew, like this? Watch it again and pay attention to the top of the coil. You will see that it moves upward through the magnetic field that points inward. Now the coil is made up of metal, and the metal has lots of free charges in it, and they're the things that move when you hook up a battery. Well, those free charges are moving up along with the coil as the coil moves. Whenever you have moving charge in a magnetic field, you get a force. The right-hand rule predicts that those charges moving up in an inward field would be pushed to the left. Now watch the same thing, but pay attention to the left side of the coil as the coil grows. If you watch it again, you see the left side of the coil moves left. In the field that points in, the free charges in the coil move to the left along with the coil. Those free charges should be pushed down by the magnetic field because those charges are moving. Now look at the right side of the coil and the bottom of the coil as the coil grows. If you watch it again, you can see that the bottom of the coil moves down and the right side of the coil moves to the right. The free charges move along with the coil. So the free charges in the bottom of the coil moving down should be pushed to the right, and the free charges on the right side of the coil moving to the right should be pushed up. If you put all these things together, you should see that the free charges are going to be pushed counterclockwise around the coil because the coil is moving. And look at any one of those red arrows and use the right-hand rule and see why we get the green force. What we get from this is a counterclockwise current because all the forces are pushing the charges to follow a counterclockwise path. It's almost like there's a battery hooked up to it. We do get a voltage. What if we took the coil and shrank it like this? You should see that the free charges would be pushed clockwise around the coil because of the motion. Because of the clockwise push, we should get a clockwise current. What if you had the magnetic field coming out of the page and the coil shrank? You hopefully see the free charges would be pushed counterclockwise because the coil is shrinking. The coil moving in the field makes a force on the free charges and makes them move. In this case, we get a counterclockwise current and a counterclockwise voltage. Now watch the two situations at the same time. All that's different is the direction of the field. In both cases, the circles shrink, but on the left side we get a clockwise current, and on the right side we get a counterclockwise current, caused by the forces, caused by the motion. Now pay attention to what's going on at the very beginning of the process, and then again at the very end. You should see, it's pretty clear, that there are fewer X's, fewer field lines inside the circle at the end of the process than at the beginning. The number of X's inside the circle is called the magnetic flux. And the magnetic flux at the beginning is big. The magnetic flux at the end is small. If I had to attach a number to the magnetic flux at the beginning, I would say there's about 11 X's inside. The magnetic flux is 11 at the beginning. So what we've seen, as the circle shrinks, that means the magnetic flux decreases, and in this case we get a counterclockwise current. We get the current when the magnetic flux is decreasing. Now, the current that the magnetic flux decreasing produces, the counterclockwise current, it makes its own magnetic field. Counterclockwise current makes a field that points at you. You can see it in red there. One way to think about this is that the clockwise current makes its own magnetic field, the red magnetic field, and it's trying to increase the flux. So in summary, as the magnetic flux decreases, a current is produced. This current tries to increase the magnetic flux. When the flux decreases, the current tries to increase it. So here we have the inward field again. If the magnetic flux decreases, a current is produced. This current tries to increase the magnetic flux. This time, it's trying to increase the magnetic flux into the screen. When the flux decreases, a current tries to increase it. What would happen if the magnetic flux increased? Well, we know from before that a counterclockwise current is produced in this situation. The counterclockwise current makes an outward magnetic field. The outward magnetic field decreases the flux. So if we change the size of the circle to increase the flux into the screen, the current will flow to try to make the flux into the screen smaller. If the magnetic flux decreases, a current is produced. That current tries to increase the magnetic flux. If the magnetic flux increases, a current is produced. And that current tries to decrease the magnetic flux. So these rules, put together, give them a name. The first one's the law of induction. A change in magnetic flux through a loop creates a voltage around the loop. That's called the induced voltage, or EMF. If there is a voltage around the loop, there would be a current around the loop. If that current exists, you call it the induced current. That's part one. Part two is called Lenz's law. And it says that the induced voltage will act so that it opposes the action that produced it. If you have an induced current, it's going to make a magnetic flux that is opposite to whatever it was that created it. Now this is really complicated, weird stuff. You need to practice. So the other videos will show you ways to use this rule, and tomorrow in class we'll do even more practice so you get really good at it. Thanks for watching.